Everyone here, welcome. I want you to imagine it's 2050 and the final FIFA World Cup game are being played. But instead of humans running on the field, we have robots. Is it even innovative possibility today? Can you think of that? Crazy. I mean, think of it. Could machine really improve to that point where they can match or even go beyond human in the most beautiful game? Hold on your thoughts, because by the end of this presentation, I will change your minds. Our journey today has started 5 years ago. With that being said, my name is Muda Ibrahim, and as a team leader for the work of the Robocup 2024 project, welcome you. This project presentation, where innovation meets ambition, and where we lay the foundation for the new world of innovation. The program for today, I know it's really hard to see, but the program for today will be background, which I will go through with you to ensure that you follow with us when my colleagues go through the hardware components we chosen and the software methods we used. Then I will come back to you to wrap everything up to you and answer your questions to ensure that you understand everything. Next, we will have a short demonstration of our robot that we actually built. And you can see inside the room after this presentation. We'll take it one more time because it's hard to see. So I mentioned Robocop twice, at least. By raising hands, anyone of you, not from my team, anyone of you knows what a Robocop is? One hand, two, three. Few, a lot of you don't even know what a Robocop is. I expect it. Shortly, very shortly, Robocop is a competition designed to foster research for robotics and artificial intelligence with the ultimate vision to compete in the FIFA World Cup 2050. Very interesting. So this Robocop have different league, small size league, middle size league, big size league, etc. We chosen to try to compete in the small size league, which we call SSL. There you can see a quick picture. We have 2 teams, 6 robots in each teams. We have a golf ball. It's really hard to see. It should be there somewhere if you see. We will show it in further slides. So SSL requires that we, as mentioned, requires that we have 6 robots that automatically play football, which required advanced algorithm for decision making, multi-robot coordination, and real-time problem solving. For that, we also focused on the communication. We wanted to improve the communication between the robots. Then we wanted to improve the vision system to see the ball and the robots around clearly. Lastly, to improve the decision making, which is the AI, to take a decision, different decision in different situations during the game, hopefully right decisions. Our goal was to build one robot to successfully verify it and validate it. We will see if we came that long in further slides. And I'm also pleased to mention that we had collaboration with Colombia and Panama. Teams from these countries were help us to solve problems and actually to get one step further to the new world of innovation. With that being said, I'll leave the word to hardware responsible.
Hello, my name is Pontus, and I've been working alongside Muller and as the hardware team leader, leading the hardware team in developing the robot. And today I will walk through how our robot functions and the components behind our design and how it works. So our robot needs to be able to detect other robots, needs to be able to locate itself in the playing field, and it needs to be able to sense and control the ball and also coordinate with the teammates of the robot. So to achieve this functionality, we will need to integrate the hardware with some intelligent systems, and the remainder of this presentation we will go through how we have achieved that. So to help us with our design process, we have established some design objectives which we have followed throughout the project. And the first one is that the robot must have omnidirectional movement, so it should be able to move in any orientation without having to rotate the chassis. And the robot needs to be able to manipulate the ball, which will we be doing using the kicker and the dribbler. And we will go into these components in some later slides. And the robot also needs to be able to process and sample data and make decisions in milliseconds. So real-time control is necessary to implement as well. And the design we have, when we have designed this, we have thought about it being modular. So if a component breaks, it should be easily be able to swap out. Or if future iteration on this project has some improvements, they should be easily be able to integrate them to this robot. So following the design objectives, we are using 4 brushless DC motors paired with Omni wheels in the configuration as you can see here. And this allows us to move the robot in any direction. And it has sensors as well. So sensors for detecting the other robots, and ball detection and odometry. So here are the sensors that we are used, and they were chosen in together with the team in Colombia to ensure that we could collaborate and develop the hardware interface together. So we're using some optical wheel encoders for the wheels, where we can calculate the RPM of each motor, and the motors also has Hall sensors integrated in the motors, so which is used for precise motor control using field-oriented control. And the robot also has a landing grid freedom IMU, which is used to gather data for the odometry of the robot. And it has short and long range LiDAR to detect other robots and the distance to those robots. And lastly, 2 sensors to track and sense the ball using an RGB sensor and a camera. And there's a animation of the wheel encoder and how it works. So it has 2 receivers, and a blue LED, and a disc that is attached to the motor shaft. And when the LED emits, it hits the receivers, and that way we can know which way the encoder is spinning. So we try to use off-the-shelf components to as much or wherever possible. But due to the size constraints of this robot, we were required to do some own design. So we made a custom PCB where we integrated the power distribution and the data lines from the sensors to the microcontroller, and sockets for the electronic speed controllers. We're using 5 BLDC motors in this robot, and each one requires its own motor driver. To be able to fit this in the robot, we were needed to mount them vertically, so we made an adapter for those, and these are the blue ones here. And the PCB also has 2 ports for power. This is to be able to hot swap the battery, so if one is running low, we can plug in a new one without having to restart the
Hello, my name is Paul. I've been the software lead, and we'll now go into some more details of the individual components. Starting off with the wheels, omnidirectional, as Pontus described. This means that the tiny black things here are sub-wheels. This allows the wheel to both rotate or be able to rotate in 2 directions. The sub wheels have these black X rings we used for better traction, and the wheel is made out of aluminum, except the X rings, compared to some other teams that make it out of plastic. The plastic just breaks. We have linear bearings, which we'll see now more in detail. So we have a linear bearing here made out of TPE and a linear bearing on each side made out of nylon. This helped reduce friction and helped dampen the wheels. Moving on to the kicker. As the name suggests, it kicks the balls. And it uses a solenoid. This part here, not very visible in the slides. It has 2 degrees of freedom, sadly, since the solenoid can also rotate. Optimally, it should be just 1 degree of freedom. We use 300 volts to kick, and it has no lobbing capabilities. In more advanced teams, you can see they actually are capable of lobbing the ball, which is very impressive. Moving on to the dribbler, it might not be very visible here, but it's a white bar here with a spiral form. It's used to more easily control the ball. When you spin it at up to 20,000-30,000 RPMs, it will center the ball and keep the ball attached to the robot almost. It has some ball bearings to reduce friction. It's very poorly visible. But, well, there, and there. This, once again, to reduce friction. We also can see the suspension visible here in green. It has 2 degrees of freedom, since we can both dampen in this direction and in this direction. Moving on to the software.
Thank you. Okay, software. AI, my name is Victor Eriksson. I am responsible for the AI model in this project. So we need a simulation environment, and in this case, we have here Sim. It is provided from a previous team from Amir Kabir, University of Technology. And from here, we can communicate through the local host network interface. And we can get the positions and velocities of the robots and the ball that we cannot see so clear. And also in the simulation, we can send in actions, such as rotation and velocity for each robot in both teams. Okay, so the AI model is a multi-agent proximal policy optimization, also known as MAPO. It is a reinforcement learning model, so it means it learns from its previous actions and feedback. So by this, the more it plays, the more it learns. MAPO is designed by a policy network and a critic network. And with the football terms, we can say that the policy network is the player and the critic network is the coach. And so together, both networks can be informed by the prediction and estimations to get players to achieve a teamwork strategy. How well a team performs, it's assigned by us. In our case, we have put that the distance to the ball is a negative value. So we want the players to get as close to the ball as possible to get a high reward. And then we have a demonstration here. The ball is here in the middle. So as we see here, it actually does quite kind of good, actually. But yeah, as you see, next time it doesn't. And so the thing is that we could not really verify or train this model fully because it would take a lot of training iterations. And as we've seen from previous papers, we need a lot of them. And it takes a lot of time to just do one iteration, and we're running this in just one instance. So sadly, we were not able to verify and train the model fully to see if it actually works as we want. Okay.
A critical part in our infrastructure is the use of ROS, or Robot Operating System. I now regret my choice of colors, but we use it mainly for communication, since it gives simplicity. It's very easy to communicate. We can use topics, and then we have a subscriber, which is the one who obtains the information, and then a publisher, which publishes the information to the topic. We also take benefit from its modular and reusable libraries. One of these in particular, nav2, which offers localization, navigation, and path planning, all with very good performance. And this helps save both time and effort, since we had something we knew worked well. There are two different versions of ROS we use, ROS 2 and MicroROS. We'll now see some more about MicroROS.
All right. So my name is Emil, and I've been working as a software developer, mainly responsible for IP communication and much of the hardware interface, the hardware drivers. And I'm going to talk about the software we have in place in order for our AI path planning to be able to interact with the outside world. On one end, there are external applications running on computers outside the playing field that we need to connect to. And on the other, we have the actual hardware that we need to be able to control and have the robots do the actual things and move. So starting with the first part. In a Robocop game, there are two programs running outside the playing field, on computers outside the playing field that we need to connect to. There is a program called SL Vision, and these programs, the data they provide is accessible to both teams. That provide the position of all objects on the field, robot and ball, and we have an application called Game Controller, which is operated by the human referee, and it lets us know things such as whether a goal has been scored, or a free kick, or a foul is being issued. And this data we connect to via UDP. So we developed an API to connect our AI software with this application through a UDP client. And also, during training, we made sure to develop our own version of this. Yeah, is my laser working? All right. Our own version of this game controller that is fully automated and can work without any human involvement. So we can run our AI training and simulation without oversight. Looking at the simulator happens to be designed for remote connection in mind. So connecting towards it works in a similar fashion to UDP. Now, at the other end of the information flow, we have our hardware and control over it. And at the center of all our hardware components is a microcontroller on a Nucleo development board. It is communicating with our hardware modules through various protocols. And all our low-level hardware control is running on it, and then we have higher-level applications running on the Raspberry Pi. Now, we had less than 3 months of development, so in order to cut time, we integrated several open-source third-party drivers, which is good, so since we want to avoid reinventing the wheel whenever possible. And finally, in order to connect low-level code on the microcontroller, the high-level one on the Raspberry Pi, we use a middleware called MicroROS, which sends data over UART and makes it directly accessible as in the form of ROS topics on the Pi, which is very convenient. And now, more about the mode of control.
We have both two categories of motors. We have the dribbler motor, hopefully visible there. And we also have the wheel motors visible. So the dribbler motor is just controlled using simple PWM or pulse width modulation. However, we wanted better control for the wheel motors, so we employed field-oriented control. Here is an animation of how field-oriented control. We have a poorly visible vector here that should be gray, and it's the rotor vector. In motors, we have the maximum torque when the stator vector, which is the gold or brown here, is perpendicular to the rotor vector. The stator vector is made up of the sum of the colored or the current vectors of the windings, which are the colored in red and green. So field-oriented control uses a transformation, which is outside the scope of this presentation, and then a pit controller to force these currents to make the stator vector perpendicular to the rotor vector. Moving on to the middleman software, which runs on the Raspberry Pi. The Raspberry Pi code does many tasks. Amongst them is aiming and shooting. When we get a command from the AI that we should shoot to a target, we have to ensure the robot is angled towards the target and then send a command to the hardware interface that we want to shoot. We also have to do computer vision, so we can recognize the ball. And then we also do sensor fusion of mainly the different odometry sensor information. We also have localization of the robot. This is mainly because the SSL vision has some flaws. And this localization is done using adaptive Monte Carlo localization. We have local path planning, the DVB algorithm. It's what NAV2 calls their DVA algorithm. It's an extension, so it works for omnidirectional platforms. And then we have their version of a global path planning algorithm called SMAC Planner. It uses A star. The last four, so sensor fusion, localization, local path planning, and global path planning, are all thanks to ROS and NAV2. We will look at a demonstration of how adaptive Monte Carlo localization works. So we have the true robot position as the blue square moving in an arc here. Then we have all the little dots that just seem to do random stuff, but first they are randomly distributed all over the state space. However, eventually they start to figure out what the true position is. We can see here that sometime in the middle of the animation, it seems to center around 3 positions. Starts to center around these 3. But eventually it figures out the true position. Here we have dynamic window approach. It accounts for the physical limitations of a robot. And from these physical limitations of the robot, it samples velocities and then projects these velocities to gain trajectories. We can see these trajectories in these, once again, poorly chosen color lines. They are supposed to be gray. So these gray lines that emanates from the robot, and then it scores them and chooses the best one. In this case, the best one is the green here. Here, for those unfamiliar with A-star, A-star uses a heuristic, or starting with the red is the goal, and the green is the start. And A-star uses a heuristic to search only in the direction of the goal. So the blue ones are the ones we have searched. So as we can see, it always moves towards the goal, rather than some other global path planning algorithms like that would search everywhere. That would search everywhere. This is more optimal.
Thank you. Very well, very well. Focus now because one of the most important part is coming. What can we conclude of all that? What did we do? So, as I mentioned at the beginning, we want to lay a solid foundation, a solid ground for the next groups to be able to continue developing this project, these robots, to do something with it. Because actually, it is true that we are the first group in the last decade in MDU that done this project. Very interesting. I can say that we successfully laid a ground or a foundation for the next group that continue developing and not need to redevelop anything we have developed. So that's a huge success for us. We also have some recommendation for the next groups. What do we recommend that they do next? We believe communication is a critical part of this project. We actually wanted to use Wi-Fi. I believe everyone here heard of Wi-Fi once, at least. We want to use Wi-Fi in the game. Then we discovered we will have so many distractions. It won't work, basically, if we don't have NASA advanced components. Cost millions. However, we recommend that we further investigate radio frequency communication. See what happened there. We didn't investigate it. We had no time to look at that. Further, we used Mapo, as Victor mentioned, and Mapo showed us some results, as you also demonstrate with your AI. We believe Mapo should give a good result if we have a better computer that can train the AI algorithm. So we also recommend to look further on that. Finally, this is a picture of my lovely team that worked in this project hard. You will find them around here, hiding somewhere in the corner. And lastly, I want to say that today, my group, my teachers, everyone that contributed in this project, shared their journey to build smarter, faster, and more collaborative robots to ensure that they will be used not just in a soccer project, but for the technology as a whole. So I want to leave you with the same question we started with. Do you believe that Robocop will be able to compute and win against the best team in a football game in 2050? No answer needed, just think about it. Thank you.